Hello everyone, it's Mr. Phillips Carey or Mr. PC. I prefer Mr. PC, so call me Mr. PC here, and I'm going to teach you today about uncertainty and error. So what I need you to do right now is to go out and get your spiral notebook and a pencil, and then join me with a lovely lesson on uncertainties and errors. So error is when you are measuring stuff in the lab or you're taking lab measurements. So we need to figure out in lab, and this is what I'm going to tell you from this point on, in lab, no measurement is exact. And there are three factors to that. You either have human error, which is a not acceptable experimental error and should be included in your lab report. So if you messed up somewhere in your lab, you need to make sure that you are stating it. You also have random errors and systematic errors. So when a random error in experimental measurements are caused by unknown and unpredictable changes within the experiment. They can occur in the means of the measuring instrument or the environmental conditions that the experimental is in. If you have too high or too low of an approximation of reported values in an experiment, this is known as random error. So let's think about this. If you were to conduct a lab that is supposed to be, conducted in a very hot setting, but your room is freezing, then that could be contributed to random error. You should probably change those conditions in order for the measurements to be more accurate. However, random error can be reduced by repeating those measurements. So if a reading was to be too high, it would be balanced by those that are too low in order for you to have sufficient readings taken. So for example, I have a piece of magnesium that I weighed out 6 times, and the following results are 0.1234, 0.1232, 0.1233, 0.1234, 0.1235, and 0.1236. The reason that you want to take as many trials as possible is because you want to eliminate that amount of error that you have. So whenever you're doing labs or something, or you're going to be conducting your IA, I say the minimum number of trials that you need is 4 in order for you to get rid of that random error that you have. So you find the average and you need to report the uncertainty as plus or minus 0.0002. Okay, so you need to record your uncertainty as that. The reason for this is because if you find the range of your data, you need to make sure that you will see that the range is plus or minus 0.0004. And so your mean value will either be plus that value or minus that value. So you just half that value and that'll be your uncertainty. So once you take the mean of it, the answer is 0.1234 plus or minus 0.0002 grams because the range is going from 0.1232 to 0.1236. So that is why you take your range, you divide it by 2 when you're doing averages in order for you to get the range uncertainty for all your data. So random error is equivalent to the uncertainty of a measurement. So when you're calculating the uncertainty, the final uncertainty of random error is calculated and then is compared to the percent error. So you need to calculate the percent uncertainty and you also need to calculate the percent error in your data. So if the percent error is smaller than the percent uncertainty, the difference is obviously due to random errors, which means that you're in the clear. You just need to determine what those random errors are. If the percent error is larger than the percent uncertainty, then the random errors alone do not explain the discrepancies that are in your data, and systematic errors could be involved, which means that you probably had inaccurate measurements, equipment that didn't work, things that went haywire and wrong. So when you are doing something and your percent error is way more than your percent uncertainties, that essentially means that something is way more wrong than random errors that you cannot control. Then we get into errors that you can control, which are systematic errors. So these errors are caused by the poor experimental design, which cause the data to be skewed every single time you do it. They can fix by better equipment and having a better experimental design, but cannot be reduced by repeating measurements. If you repeat measurements when you have systematic errors, it is going to skew the data so far off it's not going to be accurate. Some examples of this are heat loss in an exothermic reaction, reading the top of the meniscus rather than the bottom, overshooting the endpoint in a titration, and counting that as a trial, and then the miscalibration of a thermometer when you are doing a lab that involves exothermic or endothermic processes that involve you to take ranges in the thermometer. So if you're not accurately taking those steps to make sure that everything is good in your experimental design, then you are going to have skewed data reports. So this is where I'm going to pause and explain. You do not need to write any of this down, okay? So when you're doing lab write-ups, which you will do this year, and I'll explain how you do lab write-ups, and experimental conclusions must take into account all systematic errors and random uncertainties that you have in your lab. If you think that anything could be a possibility to your error, you need to include it. It is important when you're going to report your data. You should recognize that if one measurement has much greater uncertainty than one of the other measurements, then this is going to have a larger effect on your uncertainty for the final result. Meaning, if your one data point is a complete outlier, you probably should take another data point instead of including that in your data, because your data is going to be skewed by that outlier. So instead of having 4 data points, take another one, because you don't want your data to be fully skewed by that one. And be sure to evaluate all your experimental procedures to discuss how to reduce those systematic errors. You don't want to get down the line and be like, oh, I need to calibrate the thermometer here because it's going to, in fact, cause the systematic error that I don't need to account for. So you need to make sure that you keep all of those things intact. And this brings up the discussion of accuracy versus precision. So these are not used as interchangeable terms. They mean 2 different things. Accuracy is how close to the true value you have. Accurate measurements have small systematic errors and give a close value to the expected value. And then precision refers to the repeatability of that measurement. So whether you're able to get the exact same measurement over and over again, and this will have small random errors and are reproducible in repeated trials. So if you repeat relatively roughly the same value, it's going to be reduced. And this indicates how many significant figures that are going to be used in a measurement. So take the bullseye example. If we're right on the bullseye, and we have all our data points right on the bullseye, we're accurate and precise. But if you're nowhere near the bullseye, but your data points are close together, you're precise, but you're not accurate. Okay, so think about that. If your data points are close together, but they don't match what your research is saying, you're precise, but you're not accurate. Okay, if you're relatively around where the data points and research reported, you're accurate. But if your data points aren't close together, you're not precise. So the same thing examples of like your points are around the bullseye, but they're not close together. If your points are not close together and nowhere around the bullseye, you have more errors than you could even imagine. Okay, so you should probably go back to the drawing board and really think about what happened and probably redo the lab over again. So, how do we report uncertainties? What if we have a digital instrument or an analog instrument? How are we going to report those uncertainties within the lab in plus or minus values? So, when we take digital instruments into account, the uncertainty of the digital instrument is written by the plus or minus the smallest scale that you could possibly get. So if a balance that reads to 2 decimal places, you would have an uncertainty of plus or minus 0.01 because it goes to the second decimal place and it probably has a plus or minus 0.01 uncertainty. If a thermometer only reads to 1 decimal place, then you only have it going plus or minus 0.1 as an uncertainty. So here's an example. I have a balance that reads to 2 decimal places, so therefore you would determine the uncertainty as plus or minus 0.01. And so therefore, when you're recording this as your data in your lab, you're going to record it as 5.67 plus or minus 0.01 grams. However, what happens if you're reading a burette or a graduated cylinder? This is an analog uncertainty. So non-digital devices have an uncertainty of plus or minus half the smallest division. So if a graduated cylinder has a smallest division of 2 milliliters, then you would have an uncertainty of plus or minus 1 milliliter. Make sure that you're recording your data points as what you have for your significant figures, okay? So you're always going to want to have two significant figures here because you're going to record it and estimate the decimal point after. Okay, a ruler that has 1 millimeter divisions would have an uncertainty of 0.05 centimeters, not centimeters, millimeters. Need to have the right units there. I apologize. So you're taking the division that you have and dividing it in half. So looking at a graduated cylinder above, you can see that the obvious recording that you would make is 32.0 milliliters. However, looking at the graduated cylinder, you have 1 milliliter divisions there. So since you have 1 milliliter divisions, you would record that uncertainty as plus or minus 0.5 milliliters. And therefore your measurement would be 32.0 plus or minus 0.5 milliliters. Now, we need to ensure that our lesson on significant figures will be coming back with all of this data. So let's review. Adding and subtracting, the answer needs to match the least number of decimal places. Multiplying and dividing, you need to take the least number of significant figures that are there. Therefore, all of your data must be recorded with the correct number of significant figures. If you have an uncertainty and your data point is written as 15.00 plus or minus 0.01 on a scale, then you will not record your data as 15.1 because there's a 0 after it. You can't do that. You have to carry 4 significant figures the entire way through. So you would record your data as 15.10 plus or minus 0.01. If all of your data points have 4 significant figures and one has 3, you're not keeping track of your significant figures in the lab. So here's where I'm going to pause. We're at the 12-minute mark. I need you to go watch a video that is posted on Schoology. Watch that video, follow through with those examples, and come back. Okay, you're going to pause the video now at 12:10 and come back to it. All right, so you obviously just watched a video on how to calculate percent uncertainties and percent errors. So percent uncertainty, an uncertainty of 1 second is more significant time measurements than 10 seconds, that is more significant time of 100 seconds. So we need to determine how the significance of uncertainty can help us express uncertainty as a percentage. So the equation for percent uncertainty is your absolute uncertainty, which is that plus or minus value, divided by the measured value that you get, times 100. This should not be confused with percent error, where percent error is your accepted value minus your experimental value divided by your accepted value times 100. So the value you calculated minus the value you got in lab divided by the value you calculated times 100. Try not to confuse those two equations. I know it can be pretty difficult. So propagation of uncertainty. Consider that we have the following readings on a burette. We have an initial reading of 15.05 plus or minus 0.5 milliliters and a final reading of 37.2 plus or minus 0.5 milliliters. What volume should be recorded? Well, we need to take the maximum values that we have possible and the minimum values that we have possible. If we want the maximum value possible, we're going to take the initial reading, the lowest value of that, and the final reading and the highest value of that to get the maximum value possible. If we want the minimum value possible, we're going to take the initial reading and take the highest value, and the final reading and take the lowest value to get the minimum reading. So when we do that, after we find those two values, we add them together and divide it by 2 to get a mean. So we take them and divide it by 2, and then we add the uncertainties together and carry it through. So if we do that, when we're trying to get the final reading off of the burette, we'll get 22.15 plus or minus 0.1. So multiplication and division is a little bit different. So consider that we're trying to solve for the density of an object and we have 24.0 plus or minus 0.5 grams and the volume of an object of 2.0 plus or minus 0.1 grams. In order for us to find the uncertainties, we need to do the percent uncertainties first for both of them, which for the mass would give you 2%, the volume would give you 5%. Okay? Then you divide the two numbers to get the answer that you need. So 24 divided by 2 gives you 12. Here's how you find the plus or minus error that you need. So you take the 2% that you have and the 5% you have, you add them together, and you divide that by 100 to get 0.07. Then you have an equation backwards, so you have x divided by 12 equals 0.07 Do the math to get 0.8, and you're provided with the answer of 12 plus or minus 0.8 grams per centimeter.